record on this computer. Okay, so last time we were talking about, what did we finish off on? We finished the squeeze theorem, right? So maybe let's just recall what the squeeze theorem says. Okay, so the squeeze theorem said that basically if I had a function, a top function, a bottom function, and then I knew that they had equal limits at some point, then any function in between them also had to have a limit. So the limit existed and it had the same value of the limit, right? So I'm not going to state the theorem in its totality. I'm just going to kind of say, oh, look, if I have three functions, f less than g less than h, and the top and the bottom have the same limit, then the middle function does as well. G of x is equal to L, right? Okay, now I left you with an exercise. This exercise is pretty straightforward to prove, so I'm not going to prove it for you. But you definitely should, because we are going to use this. And so you need to convince yourself that you understand what it is that it's saying, okay? So the limit of the absolute value of f of x is equal to 0 if and only if the limit of the function itself is equal to 0. I think the battery on this pen might be dying. I've had to do this a couple times now. So if and only if the limit of f of x is 0 like that, okay? So in one direction here, you'll just want to use epsilon delta, and the epsilon delta proof is very straightforward. Like as soon as you just write it down, everything falls apart immediately. You basically get the absolute value of the absolute value, which is just the absolute value, and you're done. The other direction, you could try an epsilon delta it. That's probably the hard way. It's probably easier to squeeze theorem, right? Like use the fact that the function f of x is always between the negative of the absolute value and the positive absolute value, right? And then you know both of those things go to 0, and so it forces the middle thing to go to 0 as well. But this is a really nice fact because you can show that something goes to 0 if you know that it goes to 0 in its absolute value. And you might say, well, like that seems like maybe it's extra work. No, it turns out that that actually makes a lot of our lives really, really easy, because a lot of the time it's easier to bound the absolute value than it is to bound the original function. Especially think like, you know, if your original function does a lot of oscillation or something, it can often be easier to take the absolute value and then it kind of, you know, instead of needing to find a nice lower bound, when you take the absolute value, you know that it's always greater than or equal to 0, right? That might be worth writing down. So as a comment, since the absolute value of f of x is always greater than or equal to 0, maybe I should say since. So since this is automatically a lower bound for the squeeze theorem. Right? And in doing so, we haven't lost anything, because even if we show that the absolute value of f of x is, I mean, this only works obviously if we're trying to show f converges to 0, but in this case, we haven't lost anything, because if we can show that the absolute value of f of x goes to 0, then f of x goes to 0 as well, right? So this is why this is such a nice and handy tool. Okay. And yeah, like, I don't know, I guess I'll do one example. I should just show you how the squeeze theorem works. But you know, I'm certain, again, that most of you have probably seen a squeeze theorem example before, so I'm not gonna, you know, I'm not gonna go crazy. So let's do another maybe example here. So let's say show Okay, classic example. Show that this is true. And remember last time, in fact, when I was talking about the limit laws, I mentioned that this is, this was kind of like one of our caveat emptor cases, where if you incorrectly applied the limit laws, you would get 0, which is the right answer, but you did it the wrong way. And the correct way is to use the squeeze theorem. It's not the only way, but it's kind of the easiest way. All right. Now, the reason why I've chosen this example as well is because I think that a lot of like in high school, for example, I know that my teacher who taught me the squeeze theorem actually did this example wrong. Right? Because what a lot of people want to say is the following. So this is wrong. Let's just kind of preface it with big ol' wrong statement. Okay, so don't do this. I'm just kind of doing it to show you what most people think is a correct strategy. So they'll say something like, oh, well, since sine 1 over x well, maybe since -1 is less than or equal to sine 1 over x is less than or equal to 1, we have that negative x is less than or equal to x sine 1 over x is less than or equal to x, like that, right? And then they'll say, oh, by the squeeze theorem, I've got this lower function, negative x, and this bigger function, positive x. Both of those go to 0. So therefore, by the squeeze theorem, the middle thing does too, except this is wrong. And why is this wrong? Okay, can anyone tell me? Exactly. What's the sign of x? Because in particular, we are taking the limit as x goes to 0, and it's a two-sided limit, right? So sometimes, exactly, yeah, if you just plug in x equals -1, immediately you get something which is nonsense, right? If you ignore the middle piece, you'll get 1 is less than -1, and that's clearly false. So when x is positive, no problem. You can do this multiplication, and that's okay. When x is negative, though, you actually would have to flip the signs. Now, that's not the end of the world, okay? You can still do this by using the one-sided version of the squeeze theorem, right? So if you look at our proof of the squeeze theorem, you realize that same proof would hold if I approached from the left and the right individually. And so what you could do in this case is break it into cases. What happens when x is greater than 0? So I'm taking a limit from the right. What happens when x is less than 0? So I'm taking a limit from the left. Show those are both 0. And then conclude from the squeeze theorem that way, right? So you could do one-side limits. So I'm going to say we don't know the sign of x. But we could fix this by using one-sided limits. Could fix this with one-sided limits. Okay, so I am not going to use one-sided limits to do this. I recommend that you do it just to, again, sanity check yourself and make sure you can do it. And in fact, if you haven't proven the one-sided version of the squeeze theorem, and like maybe if you're like, he says it's obvious, but I don't see it, just start writing it down. And you'll see like, oh yeah, okay, this clearly just does what it's supposed to. Really, the x minus c less than delta part really doesn't play a role, right? So it doesn't matter whether I'm on the left or right or taking a two-sided limit, it's the same thing. So try that as an exercise, and then make sure you can do this one with the one-sided limits approach. So what I'm going to do, though, is I'm going to take the absolute value. Okay, so instead, I'm going to do this. So I'm going to say, since the absolute value of sine 1 over x is less than or equal to 1. And of course, that's the same statement as the since -1 is less than sine 1 over x is less than or equal to 1 statement above, right? It's the same statement. But since this is true, then 0 okay, so I'm going to take the absolute value. And like I said, in the green comment above, we automatically get for free this lower bound by 0. And now I can use the fact that sine 1 over x is bounded to say that this whole thing is less than the absolute value of x. Okay, and yeah, x goes to 0 as x goes to 0. That's like, what I'm saying there is the limit as x goes to 0 of x is equal to 0. We know that. So by the exercise above, the right-hand side goes to 0. The left-hand side is a constant. Voila. So by the squeeze theorem, and I'm going to include this just, because I'm checking my hypotheses, right? Though in this case, I would be happy if you just kind of went straight to the conclusion. That tells us that the absolute value goes to 0. And again, we would say, well, this isn't actually what we wanted to show. We wanted to show the thing inside the brackets is 0. But again, we have that if and only if statement about the absolute value. So we can conclude that, what we wanted to be true. Like so, right? Just like that. I think that's a little bit easier. Yeah, it's probably about the same amount of work as the one-sided limit. Because if you do the one-sided limits, I would say, look, let's take the limit from the right where the above bounding does work, and I would do all the work. And then I would say, as we take the limit from the left, the only thing that needs to change in the proof is we need to flip these signs, but it still does work, and so we're done. So it's the same amount of work as the one-sided limit if you're willing to kind of hand wave away one of the cases. Otherwise, when you do the one-sided limit, obviously you have two cases. And the benefit of using the absolute value is you can kind of combine those into a single thing, right? So hopefully you see here, there is an advantage to doing the absolute value, especially when we have this sign indefiniteness, right? Depending on whether, like if I'd had x squared sine 1 over x, I wouldn't have to use the absolute value, right? Because when I do the bounding argument, the bounding argument at the top of the screen, I would be multiplying by x squared, which is sign definite, right? It's always greater than or equal to 0. So the inequalities would be preserved, and I wouldn't have to use the absolute values, and I'd be done. But if I'm not using that, then I have to be a little bit more careful. And you should only need to use this for when your limit is approaching 0, because if your limits approach something like 10, then the hope is, at least, that you should be able to restrict yourself to, a neighborhood around your limiting point. Because if your limit is approaching 10, your functions are probably positive in a neighborhood around your limiting point, and you don't need to worry about this weird trickiness about signs flipping. It obviously depends on the precise bounding argument that you're making, but as a general rule, you don't have to worry about it. Okay, so really only 0 when you're approaching 0 do you kind of run into these problems. Okay, so any questions about that? Otherwise, I'm going to give you a theorem, and I'm going to write this down, and you're going to be like, why is that a theorem? And then you'll see why it's a theorem. But if you have questions about the last thing, just let me know. Okay, so theorem, sine x goes to 0 as x goes to 0, period. That's it. And right, usually we reserve the word theorem for heavy hitters, for mathematical results that have, a lot of implications and a lot of impact. And yeah, you might say, like, this seems, one, maybe kind of obvious, even if it's not obvious immediately how to prove it. But two, it might not seem obvious that, how impactful this is. From this statement, we are going to, well, you'll see how many things we get from this one statement, right? It's very, very nice. So here's the proof. The proof is, as with all things trigonometric, the proof is very geometric. Okay, so basically what I'm going to do is I'm going to break this into cases. again, I'm going to kind of hand wave one case, but hopefully you'll believe it once I draw the picture. So let's say for now, that x is between 0 and pi by 4. I actually could probably do pi by 2. Let me think. Am I going to get into any trouble? No, I think I could do pi by 2. Let's maybe go open pi by 2. Okay. And again, you might wonder why I'm doing that. I'll show you in the end. So what I'm going to do is I'm going to draw an assistive picture so that you can see the argument that I'm making. Let me just check my notes here. So I use the same picture. All right, and I'm going to take a look at the quarter circle of radius 1. This is x, this is y. And then I'm going to draw a kind of random angle x, like that. All right. So this thing here, right, the opposite side of this triangle, remember this is the hypotenuse here is 1 because it is the radius of the circle. And so the opposite side of the angle is sine x, right? So this thing here, I'm going to write it as the absolute value of sine x. But it doesn't matter because when I'm between 0 and pi over 2, this number is always positive anyway, right? We know that. Of course, the x coordinate here is cosine x. We know that, but we're not talking about cosine, so we're not going to worry about it. And so my question for you, does anyone know what this length is? Suppose that x is in radians. Right, yeah, it's x. Or in this case, again, I'm going to write just absolute value, but you're absolutely right. This is x. Because the length of a sector, maybe you might need some review of this. Does anyone remember what the formula? So for a sphere of radius r and an angle subtended by theta, the length of the sector subtended by those things is what? R theta, exactly. Perfect, perfect. And yeah, Devansh, I know you mean theta there, but theta is a pain to write, so yeah. Right? And this is kind of an important point here. Theta here has to be in radians, right? In fact, if you don't remember, this is actually the definition of radians, right? The radian is precisely defined to be the length of the sector of radius 1 subtended by that angle, right? So that's why there's 2 pi radians in a circle, because that's the entire circumference. So the definition of radians actually tells us that this is true. Okay, so that's the absolute value of x. And now without going into too much proof of it, my claim is evidently the absolute value of x, like the length of the sector is definitely longer than sine x. Like so, right? That's it. And of course I have to do this because I want to do a 2-sided limit. So I'm going to do it from the other side as well. Okay, so it's true as well if we take it to be in negative pi by 2 to 0, and that's why I'm using the absolute values, right? I'm using the absolute values precisely so that I don't have to worry about, yeah, okay, sine is negative when, I'm between negative pi by 2 and 0, but it doesn't matter. I'm going to use the absolute values and therefore get the same inequality. So that means that this inequality here is actually true on a 2-sided neighborhood of 0. So by the squeeze theorem, we're done, right? Because we know the left-hand thing is definitely 0. the absolute value of x is also definitely 0. So the middle term goes to 0, and the absolute value of sine x is 0 if and only if sine is 0. Okay, so I'm going to skip most of that and just kind of go to the end here. And we're done. Okay, but again, there's a couple steps there. You should verify that your two boundaries, or a 0 and the absolute value of x, both converge to 0. And then you should say, oh yes, by the squeeze theorem, that means the absolute value of sine x goes to 0. And then by our exercise at the beginning of class, that means that sine x is 0, right? So voila, we've proven the theorem. Okay, any questions? All right, just a nice little piece of geometry there. Makes it true. So, I said that this result is so important that it actually has the impact of being a theorem. And the reason for that is because sine is so periodic and is so sort of like well understood that just knowing about what sine does at 0 is actually enough to figure out what its limit does everywhere. Okay, turns out if you know what the sine function does at 0, you know what it does at every single point in the real numbers. So in order to show you this, the first thing we have to do is kind of figure out what cosine does. And there are many ways of doing cosine, but so corollary. Right, so remember, a corollary is something that immediately follows a previous result. So usually you prove like a theorem or a proposition, and then immediately after you prove a corollary, which uses that theorem or proposition very heavily, right? That's what a corollary is. It's like a small result that immediately follows a big one. Okay, and it's the obvious thing. It's that cos x is equal to 1. Okay, so to do this, what I'm going to say is the following. So I'm going to start by saying, listen, the limit as x approaches 0 of sine squared x, remember sine squared is sine x all squared, right? But we use this weird notation where we put the squared kind of earlier, before the left bracket rather than after it. But that's what it means. It's sine x times sine x. And we know this is 0 by the limit laws, right? Because we know that sine x is 0. And as we kind of said last time, since I know that limit exists, sine x times sine x, that limit will be the limit of sine x times the limit of sine x, which is 0 times 0, which is 0. Okay. So what I'm going to do then is I'm going to, in some sense, undress this limit and say, oh, look, that means I can say something. So let's say let epsilon greater than 0 be given. So I'm actually going to prove cosine x not with the squeeze theorem, but with epsilon delta. So let epsilon greater than 0 be given. And choose delta 1 greater than 0, such that the absolute value of sine squared x is less than epsilon. Right? So again, here I'm using the fact that I know the limit of sine squared x is equal to 0, right? I'm not trying to prove it. We already know it's true. So now I'm going to use it, right? I'm going to let epsilon greater than 0 be given. That's the epsilon I'm going to use to prove cosine. But for a reason that isn't yet clear, I'm going to plug that into the limit definition for sine squared and use it to get out a delta, okay? And that same delta is going to work for me for cosine, okay? So we claim, or actually, I'm going to have to choose a slightly different delta, but it's pretty close. I guess that's delta 1. I should call it correctly. So delta 1. And what do I want? Pi over 2. Okay, so again, this isn't me doing rough work. This is me doing the actual proof. So if at this point you're still kind of confused about why I'm doing things, that's okay. You'll see why in a second. So I'm going to take delta to be the min of delta 1 and pi over 2. And that way, and note that cos x minus 1 and if I had done my rough work first, then you would have seen me do this calculation. Okay, which is to basically boil down cos x minus 1 into a statement about negative sine squared. And in this very final step, I use the fact that cos x is positive, right? So that I can bound negative sine squared over cos x plus 1 just by negative sine squared over 1, right? And that's where the pi over 2 comes in, right? Since x is between, since I'm guaranteed, I guess I should say, and note that if, sorry, I should have said 0 is less than x is less than delta here. You can just hopefully stick that in. By assumption, this means that x is between negative pi over 2 and pi by 2. And we know that cosine is, oh, shoot, I guess I want pi over 4. So sorry, everyone, right? Where is cosine positive? Okay, I just need to draw it. Believe it or not, I still have to draw cosine in order to remember where it's positive and negative. Right? There's pi by 2. Oh, yeah, so it has to be pi by 4, right? Right, because here's pi by 2. So this is pi by 4. Yeah, so if I want cos to be positive, yeah, which is fine, whatever. After all these years, I still don't remember where cosine is positive. So pi by 4 is what I wanted, right? Because I just want to ensure that cosine is positive. So that way this inequality works, right? Does that make sense? All right. Okay, so now in terms of epsilon delta, what do we know? So again, we have 0 is less than x is less than delta. So that means that f of x minus L, right? Remember, what am I trying to prove? Look at the yellow thing at the top of the screen. I'm trying to prove that cosine x goes to 1, right? Is 1 cycle pi or 2 pi? 2 pi, right? 2 pi, sine and cosine are 2 pi periodic. So when I start at positive 1 and go to negative 1, that has to be pi by 2, right? And then if I come back up, that's 2 pi. Right? It's the same thing. It's like when you go around the circle, right? When you think about the angle, how many radians did you do? You went 2 pi around, right? Because you do pi by 2, pi only gets you to the opposite side, right? And then 3 pi by 2, and then 2 pi. So that gives us cos x, the absolute value of cos x minus 1 is equal to the absolute value of negative sine squared. And hopefully you'll forgive me if I just drop the negative, right? We don't need it. And that's now less than epsilon, right? Because that's what I assumed in the very beginning. I assumed that sine squared x was less than epsilon. That's how I got this delta 1, right? And so I'm done. And you could go back and you could reprove this if you wanted to. You could prove it from scratch. You could do some sort of like geometric thing, very similar to what we did with sine. And you might even say like maybe that it looks like less work. I actually don't think that this was a lot of work. It just kind of looks like a lot of work. You know, anytime you're dealing with trig functions and you want to relate one trig function to another, you're obviously going to have to do a little bit of, you know, algebraic or trigonometric algebraic manipulation, right? So in this case, I knew I wanted to relate sine and cosine. There was going to be some algebra there. Even if you go, and I'm pretty sure even if you do it algebraically, well, you might be able to avoid using anything about sine. But I think the argument actually gets quite nasty for cosine. Like it's not as nice as it is for sine, right? So just, keep that in mind. And in part because the limit here doesn't go to 0, right? Which means we don't get to use this like nice absolute value trick when we're doing cosine. And if we do, it's a little bit harder. So is it cos? Yeah, that's cos x minus 1 is less than, oh, you're right. It should be less than or equal to. Thank you. Yeah, you're absolutely right. Okay. So I use the fact that sine x is 0 in order to prove that cos x is equal to 1. And now from those two things, I have everything. Or I guess this is another corollary. Okay, so for every real number, you can evaluate the limit of sine just by plugging it in, and you can evaluate the limit of cosine just by plugging it in. For those of you who remember what continuity means, this is basically the statement that sine and cosine are everywhere continuous on the real numbers, right? And all I need is the fact that sine x is 0 and cos x is 1 in their limits, right? That's it. That's all I need. So I'm going to do the first proof. The second proof is exactly the same. And I'm really hoping that I remember the angle sum identity, but I'm certain one of you does and will tell me if I'm wrong. Because here's the problem. I'm not going to lie to you. You know what I teach? I teach Math 133 and Math 257. That's all I taught last year, right? Math 133 doesn't have trigonometry. Really, neither does Math 257, which means I haven't done trigonometry an entire year. So I've forgotten all my identities. So if I screw up the identity, you need to tell me. I guess this is a proof, not a solution, so proof. Okay, so I'm going to do it for sine x, and you can do it for cos x. So the first thing we need to do is recall the following, and I say recall, but we haven't actually proven it. So the limit as x approaches c of sine x is the same as the limit as x approaches 0 of sine x plus c. Now, if you haven't proven this yet, this is very much worth proving. Okay, it's a nice little thing. We'll use it for those of you, again, who have done derivatives. You might know that often we have these two different definitions of the derivative, and one of them has, an x plus h in it. And to see that they're equivalent, it will help for you to convince yourself that this is always true. Okay, so kind of as an exercise, if you want to, prove that this is true. Right? There's nothing special about sine here. This is always true. This proof isn't too hard. Basically, write down the epsilon delta definition of the left-hand side and define a new variable. In fact, maybe it might help you not to call this x, both variables x. Obviously, it doesn't matter. But just for the sake of understanding, sometimes it helps to call it a different variable. So I'm going to call it y. Write down the variable on the left-hand, write down the epsilon delta definition on the left-hand side and define a new variable in a clever way. And you'll just see that if you then replace all the x's with the y's, you get exactly the definition on the right-hand side. So there's nothing to prove. So it's 1 or 2 lines. It's very straightforward, but you should prove that yourself and convince yourself that it's true, okay? And the reason that I do this is, like I said, I want to use the angle sum identity, right? I know what sine x plus c is. It's sine x cos c plus cos x sine c, right? Okay, so this is me being rather arrogant because, believe it or not, I didn't look this one up, which is why I need you all to tell me if I screw this identity up. but I'm pretty sure I got that right. Right? Hopefully that looks right. And assuming that it is, cos C and sine C, those are just constants, right? So they're constant functions. We don't care, or in fact, they're the alphas, right? They're just scalar multiples. So we don't care about them. So the only two things that we're actually limiting here are the sine X and the cos X. And I know what those limits are. So by the limit laws, this becomes cosine C plus sine C like that. And I know exactly what these two limits are. Sine is 0, cosine is 1. So almost everything dies. The only thing which survives is sine C. And so this is what I'm saying about the impact of that result, the fact that sine X went to 0 as X went to 0, right? And I called it a theorem. And you might say, well, why did you call it a theorem? Because immediately from that one result, this is what I want you to think about, how profound this is. From that one result, I now have the limit of sine and cosine at every point. If I know the value of the limit of sine at one point, I bootstrap that to figure out the value of sine and cosine, their limits at every single point, right? And so it's really ends up being quite a profound and very powerful result, right? I was immediately able to do a whole bunch of crazy things with just that result. Now, like I said, I didn't actually prove the cosine one for you. You should do it, but you imagine the identity, it works the exact same way, right? You say, look, the limit of cosine X is the same as the limit of cosine X plus C as X goes to 0. Now you have to use the cosine angle sum identity, but that's not that hard. And then exactly the same thing, you're going to get a bunch of sine X's, cosine X's, sine C's, cosine C's, use your limit laws, everything will die except the cosine C term, and voila, you're finished, right? So the proof is exactly the same. It's just everywhere there's a sine, you'll put a cosine, and then you'll use the cosine angle sum identity, right? But otherwise it's identical. So I'll let you try that one on your own. Just write it out very quick. Don't even if you don't write it formally, just write it very, very quickly. Can this also be applied to other functions that can be evaluated directly? What do you mean, Jinjin? So it's an interesting question, but do you mean like other trigonometric functions or just other generic functions? Because you'll see the critical step here that was very special to sine is this equal sign right here, right? It was very critical that I was able to write sine X plus C as some other term, right? Now, depending on what function you're given, there might be something you can do. For example, when we eventually start talking about the exponential function, and in case you didn't know, this is not an early transcendentals function class. So you'll notice I've never talked about the exponential or the logarithm yet, but there is something you can do in terms of the exponential and the logarithm and make similar sorts of arguments, right? Because we know properties of those functions. So if you want to do something like this, you need to know enough about the function that you can manipulate it in some way in order to actually be able to relate. Yeah, let me say it like this. The critical point that I used here is that I could relate sine C back to sine X using some sort of trigonometric identity. And that's what this angle sum identity let me do, right? It let me relate sine C back to sine 0 in some way. If you have a function, some other function which allows you to do that, then yes, you can take advantage of this and you can do exactly the same sort of thing. But certainly not every function will let you do that. And some functions might, but you just don't know enough about them. So it really depends on the function. In this case, the trig functions are all very well behaved. We understand them very, very well. And so we're able to say these sorts of things. You might not be able to do it for others, right? This is something that's fairly special. But if you want, a fun thing to do now So immediately as well, note that this proves tan, right? So anywhere where cosine is not 0, we now also have tan is continuous as well, because once you have sine and cosine, you have all the classic trigonometric things, right? You've got secant, cosecant, cotangent, tangent. So now I know these, I know the limits of all the trig functions. And sort of like comment with the limit laws, we now know the limits of all the classic trigonometric functions. Okay, there's a little bit more to be said about things like the things where the denominator can be 0, secant, cosecant, tangent, all these sorts of things. There's a little bit more to be said, but I think actually in your assignment 3 extra problems, I have you prove that if you have a limit that's like a division law, so you have f of x divided by g of x, you know that f of x goes to something not 0 and g of x does go to 0, then you can prove that that limit doesn't exist. So in particular, we can very quickly conclude that, yeah, those things have some sort of vertical asymptotes. So there is a little bit of work to be done there, but not a crazy amount of work, right? But otherwise, we now know lots of things about all the trig functions, right? So I think that's pretty nice. All right. So I did leave you with a bunch of exercises today, right? So let's kind of let's kind of recap them. So here's an exercise that I think you should do. All right, this yellow box here. All right, and again, it shouldn't take too long. It's a couple of lines. You might need to think about it, but it's not too bad. Where's the other one? Oh, I guess I left you with. Here's another exercise. Right, showing that cos x goes to cos c. That one's not too bad though. Okay, but it's another exercise. Where else? What else did I give you? If you want, you could do the negative pi over 2 to 0 version of this. But again, it's the same picture, but reflected in the x-axis. And when you take absolute values, you're like, yeah, obviously it's the same picture. Oh, here's an exercise, right? To do the one-sided version of this. Again, it should be quick, right? None of these exercises are meant to be terribly long. Should be quick. And this exercise that was originally up here that I didn't prove for you either. So I think that's 4, but none of them are meant to be long, right? But remember, when I do give you an exercise to say, you know, make sure that you've tried this, I do mean it, right? Like it's not just sort of like this is something that you can do for fun and not worry about it. Sometimes those things will happen. But when I leave you an exercise and say you should try this, it's because I legitimately think there's value in it. And I may lean on that, you know, at some point in the future. And you've seen this before, right? Remember, I think I had you all prove what did we do? We did injective if and only if left inverse, right? And then I said prove surjective if and only if right inverse, and bijective if and only if two-sided inverse. And it actually really helped to know those things on the term test and for the assignment questions, right? Assignment 1, question 2, it would have helped to know bijective if and only if two-sided inverse. And for the term test question 3 with the courageous function, it would help to know injective implies the existence of a left inverse, right? Well, I guess we did actually prove that one, so you didn't need to do any exercises there, but nonetheless, when I say to do these exercises, I mean them, okay? So there are only a couple here. We're gonna end class here. In fact, maybe we'll end a couple minutes early, and then what you should do is you should spend 10, 15 minutes, especially if you don't have a class immediately after, and just see if you can knock these things out, right? Just as good little practice somewhere. Okay, so give that a shot. Are there any questions? Otherwise, I think we can call it a day. And actually, I can't hang around too long because I have a damn meeting right at 10 because today's not a super busy day. A function that is not locally bounded, bug Yvonne, because Yvonne did actually come up with a correct example. There's a little bit that actually needs to be done to prove that Yvonne's example is correct, but Yvonne's example from Tuesday is exactly a function. Yeah. Yeah, and he put it in Discord, so give it a shot there and take a look at it there. Okay, anyone else? Yeah, sweet. That's awesome, Yvonne. Yeah, totally throw that proof up because and you know, everyone, if you want to prove it too, don't necessarily look at Yvonne's proof until you kind of want to check your thing as well, right? Because it's a fun little exercise to do on your own. Is there a link for the Discord? I mean, I can try and pull it up really quickly here because otherwise, normally I would just say whatever. But if I close the meeting, no one's going to have access. Maybe somebody's faster than me. There you go. So make sure you do that because I'm going to close the meeting here quick. So. Okay. All right, everyone. Thanks. Remember, next week is reading week. We don't have anything next week. Don't come to lecture. Don't go to office hours. Don't go to tutorial. Nothing like that. Catch up on your courses, including this one if you need it. And otherwise, have a good weekend. Have a good break. And I'll see you in a week and a half or 2 weeks or however long it is. Okay? Thank you, everyone. And I'll see you later. See you, everyone.